The diagram shows the curve y equals sine 2x over x plus 2 for x from 0 to pi over 2. The x-coordinate of the maximum point M is denoted by alpha. A. Find dy over dx and show that alpha satisfies the equation tan 2x equals 2x plus 4. The first step is to find dy over dx for y equals sine 2x over x plus 2. Y in this case can be divided into two functions, the function on top and the function on the bottom. So we can use the quotient rule to differentiate this by letting u equal sine 2x and v equals x plus 2. If u equals sine 2x, du over dx is cos 2x multiplied by the differentiation of the inside, which is 2x. Therefore, the differentiation of 2x is 2. So therefore, du over dx is equal to 2 cos 2x. And if v is equal to x plus 1, then dv over dx is just equal to 1. So we can substitute u, v, du, and dx and dv over dx into the formula for the quotient rule to differentiate it and get dy over dx. Then after simplifying everything, we get dy over dx equals 2 cos 2x over x plus 2 minus sine 2x over x plus 2 squared. We are trying to find an equation that alpha satisfies, and alpha is the x-coordinate of the maximum point M of the graph, and we know that for any maximum point, the gradient is equal to 0, so we're looking for dy over dx equals 0. So what we can do is set the expression we got for dy over dx to equal to 0, and then we should be able to rearrange it into the equation that the question wants, which is tan 2x equals 2x plus 4. If you look at the expression that we want to rearrange it into, it has no fractions and it has a tan term. So what we want to do is get rid of the fractions and then turn the sine and the cos into a tan. The first step, we can get rid of the fractions by multiplying both sides of the equation by the lowest common multiple of the denominator of both fractions. So that's multiplying both sides by x plus 2 squared. The next step is to turn the sine and the cos into a tan, and we can use trigonometric functions to do that. The trigonometric function that we often use is tan theta equals sine theta over cos theta. We have a sine 2x in the expression, so if we divide that by cos 2x, we will get tan 2x. And what we do with one expression, we need to do with every other expression as well. So we need to divide everything by cos 2x as well. And then if we simplify that, we get 2 multiplied by x plus 2 minus tan 2x equals 0, which we can rearrange by moving tan 2x to the other side to get 2x plus 4 equals tan 2x, which is exactly the expression that the question wants us to rearrange it into. B. Show by calculation that alpha lies between 0.6 and 0.7. From part A, we already know that alpha satisfies the equation tan 2x equals 2x plus 4. If we move all the terms in the equation to one side, or if we move everything to the left-hand side, we have tan 2 alpha minus 2 alpha minus 4 equals 0, where alpha is the root of this equation. And roots are where the equation or the curve crosses the x-axis. So if we let fx equals tan 2x minus 2x minus 4, when we want to show by calculation that alpha lies between 0.6 and 0.7, if alpha is the root, then the graph of the function f will cross the x-axis somewhere between 0.6 and 0.7. So you can expect there to be a sign change when you substitute the function with 0.6 and 0.7 when it crosses the x-axis. It will go from negative to positive or positive to negative. So if we substitute the function with 0.6, we get minus 2.628. And if we substitute the function with 0.7, we get 0.398. And as you can see, one of them is negative and one of them is positive. That means that somewhere between 0.6 and 0.7, the graph of the function f crossed the x-axis, hence the sign change from negative to positive, and therefore there must be a root somewhere between 0.6 and 0.7. And this proves that alpha lies between 0.6 and 0.7. C. Use the iterative formula xn plus 1 equals a half inverse tan of 2xn plus 4 to find the value of alpha correct to 3 decimal places. Give the result of each iteration to 5 decimal places. The question doesn't tell us which value of x to start with or what value of x0 should be, but in the previous part of the question, it asks you to prove that the solution or alpha lies between 0.6 and 0.7, so you can use 0.6 or 0.7 as your starting x value. So what we do is, to get the next iteration or x1, we substitute x0 into the iterative formula. And once we get x1, we will substitute the value of x1 into the iterative formula to get the value of x2. It's annoying to keep typing the formula out every time, so make use of your answer button in the calculator. Right now, the answer button is equal to x2, right? The answer button is equal to 0.69352. So you want to set up the iterative formula using the answer button by typing half inverse tan of 2 multiplied by answer plus 4 and close bracket. Once you hit the enter button, you will get the value for x3. And now your answer button is equal to x3, which is 0.69363. And all you need to do now to find x4 is just hit the equal button again. And the same for x5 and f6 and x7 if you need to. So it's a lot faster this way, so you don't have to type the equation again and again. The question wants alpha to 3 decimal places. So once the iteration has the same 4 decimal places, so x3 and x4 have the same 4 decimal places, so we can stop there and we can round the answer to 3 decimal places. So alpha equals 0.694 to 3 decimal places.